Alright, hi guys. Let's talk about our next set of notes for this section, being still talking about graphing rational functions. The only thing is, last time we talked about asymptotes, but there's another type of, situation that could create discontinuity. And thinking about what discontinuity means, it's exactly how it sounds. It means you are not continuous. So there's a break. So there's a break in our graph. That's a way to think about having discontinuity. So last class we talked about two types of discontinuities. We talked about the horizontal asymptote. That's always going to be in the form of y equals some number, right? Because it's a horizontal line. And it will always match our end behavior, which we've talked about since quarter one. The other type of asymptote and discontinuity we can get is the vertical asymptote. Right? It's a vertical line, so it's always going to be in the form of x equals a number. And that tells us what x can't be. Because last unit we talked about why we can't have 0 in the denominator, so we got restrictions. We were essentially finding vertical asymptotes. So you were doing it, you just didn't realize it. Let's look at our first example. Our first example says, here's a graph. What are all the types of discontinuities that you see? And basically, what are your asymptotes? So I can see here that there's 1, 2 dashed vertical lines. So I know there's 2 vertical asymptotes. And then there's 1 horizontal dotted line. So there's 1 horizontal asymptote. You'll never have more than 1 horizontal asymptote. You'll either have none or 1. That's it. So our vertical asymptote is x equals. Let's look at this one first. So I'm going to count to where that x value is. It's at -3. The next vertical asymptote is right here. And that's at also +3. Now we got to look at the horizontal asymptote. It's horizontal. And count it up. It's right there at 1. And that's it. Those were our discontinuities. Now let's look at the second one. The second one says the same thing. There are no dashed lines, but you can clearly see the graph breaks up into 2 sections. So looking at it, I can kind of see that this is our first barrier. So it's going to be x equals 0. That's our vertical asymptote. And then it looks like they never crossed this line. So that's our horizontal asymptote at y equals 0. And this one only had 1 of each. Okay. So let's look at example 3. It says, what can x not be in these cases? So basically, if we're asking what x can't be, we're asking for the vertical asymptotes. And if you look back to the first page, you take your denominator and you set it equal to 0. Add 3 on both sides. We've done this 1,000 times. We get x can't equal 3. And that's our vertical asymptote. The next one, take your denominator, set it equal to 0. There's nothing to solve, so done. So vertical asymptote is at x equals 0, which would look like our second example on top. So we talked about that last class. There's one other type of discontinuity we can get in these functions, and they're called holes. Right? That's where you have a break in the graph. So if you're going, instead of a whole line barrier, it's just one spot. Sorry guys, that was an announcement. Let's continue. So we can get just one little spot where we can't exist. An asymptote is an entire line that goes on forever, but a hole is just one certain spot. Let's just jump right into it. An example of a hole, we're going to have this picture. It says type it in your calculator and try to plug x equals 4 in. Well, and if you do that, it'll give you an error. All right, let's go see why. So the steps to making sure, 1, do you have a hole? And 2, where is this gap located in our graph? Step 1, surprise, surprise, factor. that doesn't go away. So factor both the numerator and denominator, so the top and bottom. So x squared minus 16, hopefully you all recognize, it's the difference of a perfect square. So we get an x plus 4 and an x minus 4, because the square root of 16 is 4. And we can't factor the bottom because it's already in factored form, so I'm just going to write it as x minus 4. That was step 1. Step 2, we did last unit, divide out the common factors, which basically means cancel out stuff. So I noticed there's an x minus 4 on top and bottom. That cancels out, and what we're, left with is x plus 4 on top, and whatever was on the bottom got canceled out, so we got 1, which means we're left with x plus 4 as a simplified fraction. When stuff cancels out, that indicates you do have that gap in your graph, that discontinuity, the hole. Right? Anytime you cancel even just one thing out, you've created that gap. Next up says write down the factor we divided out. So what did we cancel out? So we canceled out the x minus 4. So I'm going to take the x minus 4 and set it equal to 0. Right? Step 4 says solve for x. We get x equals positive 4. And then plug it back into the simplified fraction. So plug it into what we got in step 2. So in step 2 we had x plus 4, and now we're going to plug in our answer in step 4 in for x. So we get 4 plus 4, which equals 8. So we get y equals 8 and x equals 4. That's where this is located, at the point 4, 8. So if we graphed it on like Desmos or your calculator, right, y equals x plus 4, that's a, a linear line. But there's a hole at 4, 8. So if I eyeballed it, 1, 2, 3, 4, 8 will be somewhere here. Your graph will look something like this. This is a type of discontinuity because if I trace it with my finger, I can't go through this gap. So I pick up my pen, jump over it, and then continue. So this is another type of discontinuity you can get in addition to the asymptotes. Let's go ahead and flip it to the page, next page, and do some practice problems. All right. So points of discontinuity. Find out if we have it, and then once we find it, we write the domain. So let's go ahead and do step 1. Factor like always. Can't do anything to the top, but I'm going to add parentheses because I can. And I'm going to factor this. You can use the tree method if you need to. It's 1 and 3, minus and minus. And let's see. Nothing cancels out. This is a plus 3 and this is a minus 3, which means there's no hole, but we still have stuff in the denominator. So that means we're going to have vertical asymptotes. So we have vertical asymptotes, and what we do is we take the denominator, set it equal to 0. So we have x minus 1, I'm going to set it equal to 0, and we have x minus 3, set it equal to 0. We get 1 and 3. These are the vertical asymptotes, the discontinuities, and based on that, we are going to write our domain. The domain is always based on vertical asymptotes and the holes. Always start with negative infinity, and we go until we hit our first break. So our first break is at x equals 1. We put union because there's another section to our graph. Once we jump over 1, we keep going until we hit our next gap or break, which is x equals 3. Then there's another section, so we're going to do union. We jumped over 3, and then we go on forever. So we don't even need to graph this to figure out the domain. If you are confused, you could always graph it and then just follow your finger until the breaks, and you would write this out. Okay. Horizontal asymptote, that's when you reference your chart from last class, and we look at our highest degree on top and bottom. So I'm going to look at my highest degree here. It's a 1. And my highest degree is a 2. So this is bottom heavy, right? Mr. A says Bobo. So if it's bottom heavy, then, let's see, bottom heavy, then our horizontal asymptote is always just y equals 0. Okay. Let's do 2 more examples for this. So find the horizontal asymptote and the end behavior. Remember, horizontal asymptote matches the end behavior. So this, if you look at the chart, has a +7. You could just automatically know that the answer is 7. Or we could find a common denominator of x plus 1. I'll do my work down here. 2 over x plus 1 stays. But now we on top get 7x plus 7 because we distributed. And I'm going to go ahead and combine my like terms on top. This has a common denominator of x plus 1. And now we have 7x plus what, 9? Yep. Right. So now if we look at our degrees, we have a 1 on top and a 1 on bottom. Those are the same, you guys can't see, those are the same degree, which means we're going to make it a fraction with the coefficients in front, which is 7 over 1, 7. So we know our end behavior and our horizontal asymptote is at 7. You could do it this way, or if you look at the chart, it's as if you have a fraction plus any number. That number is going to be your horizontal asymptote. So we didn't need to do all that work. It's just one less thing to memorize if you do the work. Okay. So the range, if we graph this, I will try and let you guys see. So if we try to graph this, I know there's a vertical asymptote, x plus 1 equals 0, negative 1. So I'll put my vertical line here. And there's a y-intercept at 7. So this is 7. Not a y-intercept, a horizontal asymptote. Then if you plug this into Desmos or your calculator, you'll see the picture looks something like that. Notice how we don't cross or touch the asymptotes. So now if I do my range, start from the bottom, so we have an arrow going down, put the range here, it's at negative infinity. We're going all the way up, and then I gotta pick up my pen and come back at 7. So 7 union 7 because there's another section, and if we go up forever there's no more gaps. So there is our range for this one. Okay. Let's look at the next one. Oops, another announcement. Okay, hopefully that was the last interruption because this is the last problem. Home stretch. Let's go ahead and find our horizontal asymptote or end behavior in this case. There's nothing being added, so we just look at the degrees on top. So the highest degree on top is a 2, and the highest degree on the bottom is a 1. This is actually now top heavy, and when it's top heavy, we have no horizontal asymptote. Alright, that just means our graphs are going to go to infinity and negative infinity. Now the weird thing is if you try to graph this, right, we still have a vertical asymptote at 2, right, because I took my denominator set equal to 0. If you graph it, you'll notice you get a weird shape like this. They look like little saucers. Right. That's because there's technically a slant asymptote, and we don't cover that in our regular Algebra 2 classes. So for our purposes, the end behavior is just from 2 infinity all the way to negative infinity. That's our range. Okay? It's just the picture. If you look at it, don't freak out. So there's our actual range. Okay. And that wraps up day 2 of those notes. We just talked about graphing in general, rational functions. Next class we'll look at, I think, variations. Okay? We're done with graphing in this section. If you still need help, you can go to Khan Academy, look up resources. You can come see your teacher for help. The internet is a great place for extra practice on math. Okay? Have a good day.